So we've spent several days on particle motion in class. We have the graph of velocity measured in meters per second of a particle moving along the x-axis, so moving horizontally. So it tells us this is v of t. At what value of t does the particle have no acceleration? So what does that mean, no acceleration? Well, that means that acceleration is undefined. It didn't say when acceleration is 0. So acceleration is undefined when v of t is not differentiable, when I can't take the derivative of it. So since v of t has a cusp at time 1, 3, let's see, the next one looks like 6, and 8, there is no acceleration at those times. Express the acceleration as a piecewise defined function. So notice that the acceleration is going to be different on each of the pieces of the velocity graph. So the first piece of the graph is from here to here. Acceleration is the derivative of velocity, so it's the slope from here to here, which is 3. But it's only 3 from 0 to 1. On the next piece of the graph, this piece, the slope is -3. And that's only happening from time 1 to time 3. The next piece, the slope is 0. Slope is 0 from time 3 to time 6. From 6 to 8, my slope is again +3. And then from 8 to 10, let's see, that would be down 3 over 2. From 8 to 10. For what values of t is the particle moving to the right? Okay, so moving right, I should say particle moving right. Oh, better English if I said is moving right when the velocity is positive. So when is the velocity positive? Well, since this is the graph of velocity, it's positive above the x-axis. So this is happening when 0 to 2 and from 7 to 10. The particle is moving left when velocity is negative. And that's happening from time 2 to 7. Find the average acceleration. Average acceleration. Well, that's the change in velocity over change in time. And we're talking about the interval from 1 to 8. So I need the velocity at 8 minus the velocity at 1 over the change in time. So at 8, my velocity is 3. At 1, my velocity is 3. And the change in time is 7. That gives me 0. Velocity was meters per second. So this is going to be meters per second squared. Now we're going to define a couple of new things. Net distance and total distance. The net distance is the distance from where the object begins and where it ends. Now, total distance is kind of like your Fitbit or a mile tracker. It's the sum of all distances moved in any direction. So like when I'm walking my dog, my total distance is going to be a lot longer than my net distance. My net distance is going to be 0 because I start at the house and I end at the house. Now, what if I'm moving at the same direction the entire amount of time? Never turned around. Well, that means that my net distance would be the same as my total distance. But if I turn around even once and backtrack a little bit, then my total distance is going to be longer than my net distance. So how do we find these things? Well, your net distance is going to be the position at the end minus the position at the beginning. And I'm going to put absolute value bars because distance is always going to be positive. Now, total distance it depends on if we change directions, huh? So, if the object changes directions, at some time on that interval, total distance would be that change in position from where you started to where you changed directions plus the next leg of your trip. So you'd have to add up each of the legs of the trip. This is not a formula you're really going to need to memorize. If we're doing total distance, we have to figure out if we change directions. And then we're going to add up all of our distances. So we're given the position of a particle, positions in centimeters, and we want to find the net and the total distance that the particle traveled. Well, net distance is easy. The net distance is going to be position at 4, end position, minus the position at the beginning. So I'm going to go to my calculator and type in that function. Plus 8t. And I want to evaluate it at 4 minus the function evaluated at 1.5. And I get 58.75 centimeters. But to figure out if we ever change directions, I need to look at velocity. Velocity is 6t minus 12t plus 8. And so I want to think about, is velocity changing? Whoops, squared. So I'd start by trying to factor this. And I realized that it doesn't factor. So I decided to look at the graph. So I already had my function in y equals, because it was making it easier to evaluate. So I'm going to look at the graph. What do you notice about that graph? This is the graph of the particle, and it is increasing this entire time. So if it's increasing, then velocity is positive for all values in that range. So what does that mean? So the particle is moving right the whole time. That means net distance is the same as total distance. Here's another one. We have position function measured in feet. Find the net distance and the total distance. So net distance is going to equal P of the end, position at the end, minus position at the beginning. So I'm going to change my function in my calculator to be e to the 2x minus 8x. So I'm going to evaluate it at 1.5 minus evaluated at 0.5, and I get 9.367. feet. Now, to figure out total distance, I need to know if this changes directions. So I need to look at the velocity. So velocity is going to be e to the 2t times 2 minus 8. That's 2e to the 2t minus 8. And I want to know when that equals 0. Well, this isn't something I know straight off the top of my head. So I can first look at the graph of my position. I see that it changes directions. So I need to know when that position function changes directions, which is right here. And that's a minimum value. So I could use my calculator to find that minimum value. And it's between 0.5 and 1.5. I know that. It tells me it's at 0.693147, and I'm going to write down the whole thing. At t equals 0.693147118. So that's where it changes directions. So to find the total distance, I'm going to need to find how far I went in the first part, so 0.693 from where I started. And then I'm going to need to figure out how far I went from 0.693 to 1.5. And notice that we're putting those absolute value bars there. And I'm going to show you something kind of nifty. Since my graph is sitting on that point right now, that X value is saved in the computer or the calculator. If I press X right now, it gives me 0.693. Actually, it moved a little bit. 0.693 is a little bit off. So I can find y1 of that value, or we could type in the whole thing if we wanted to from exactly what we saw, 4718, minus y1 at 0.5, and it gave me negative 0.263456. I'm going to need the positive version of that. And then we're going to need to find y1 at 1.5 minus y1 at 0.693147118. And I want to add those two together, but I want to add the positives, the absolute values. So you can either do alpha F2 and choose absolute value of the negative one, or you could have just typed it in as positive. And I get 9.894 feet. Next one, net distance. The position at the end minus the position at the start. Minus the position at the start. If you need to see what I'm doing, I'd already stored it, so I'm just typing in what I wrote down. It gives me 0.989. Now total distance, I'm going to have to figure out if we have a change in direction. So it's always helpful to go ahead and write down your derivative. 1 plus derivative 2 sine would be 2 cosine. And I want to know when that's 0. Let's see. If I hit graph, I had my position function saved. So this is my, ooh, this is a pretty nice graph. This is my position function. And I can tell it's changing directions there, which is, looks like a minimum. But I want to make sure that's what I'm looking for. So if I hit trace and type in pi over 6, that's right there. I'm still on trace, so I'm going to type in the other x value. It's right there. So between here and here, that's my change in direction, which is a maximum. So I'm going to go maximum, get a little bit to the left, go to the right, and it tells me it's changing directions at 2.094. Actually, I'll write the whole thing. At time equal 2.0943957. So I need to find how far I went in the first part. So that would be from here to here. So the position at 2.094 minus the position at pi over 6 plus how far we went from here to there. And with a little bit of calculator mumbo jumbo and the magic of video, that's what we get.